you can actually conceptualize a computation on a quantum computer as taking a walk on a landscape. These landscapes, it's a manifold, and the manifold is what's called a Lie group. I won't go into that. But basically, to do the shortest computation, you want the shortest path. Just like, if you're walking down the shops, you don't want to take some route out back and beyond. You just want to go straight to the shop, right? And in principle, the shortest path should be the lowest energy path as well. And with classical, but also quantum computing, there are often two things you kind of focus on. Does there exist a computation to get me from A to B? Because we know from Turing that for some problems there is no computation from A to B. Like you just cannot get from A. If your algorithm doesn't hold, you will not get to B. But sort of if you ignore those pathological examples, then you want to say, does the computation exist, and is there a shortest path? So if you're on the top of the Earth, there's no single shortest path down to the South Pole, right? There's actually an infinity of paths, but there is a shortest path from like the North Pole to New York, for example. So what you want to do to have the most efficient use of energy is to estimate what the shortest path is for your computation. And it turns out that, finding the shortest path is not unlike the way that objects move in space-time. So when an object is subject to the force of gravity, what's actually happening is it's following the shortest path in curved space-time. And so it turns out that you can use the similar mathematics to try to estimate what sequence of pulses and buttons you may need to press to make your computation follow the shortest path in this computational landscape. So that was what my PhD was on.